shame being in a dark room, but whatever. And for sure, also for those who already heard a preliminary talk on the same topic last week, since Richard organized kind of a private version of this one. And so indeed, the starting point of this idea is that once you work with multivariate data, starting with dimension 2, well, the real space in dimension 2 and higher is not canonically ordered. And that's kind of a problem because it implies that such very important probabilistic or statistical concepts as a distribution function, a rank, a sign, a quantile are not canonically defined either. And I hear you protesting that you always have been told that the distribution function in RD, well, this is this probability related to south-west rectangle, which is based on marginal orders. And yes, of course, there is a distribution function sitting there. But for we statisticians, a distribution function does not come alone. It has empirical counterparts. And those empirical counterparts are extremely important from the inferential point of view. What are the empirical counterparts of a distribution function? And the inverse of a distribution function, which is a quantile function, well, the empirical distribution function basically is giving you the ranks of the observations. And the quantile, the empirical quantile are providing you with regions with given probability contents that make some sense. And if you base this on the traditional definition of a multivariate distribution function, you end up with quantile functions that are really mostly without any signification. They don't mean much, and they behave very unpleasantly under, for instance, rotations or and certainly nonlinear transformations. And the corresponding ranks, whatever you may take as a definition, the corresponding ranks, perhaps the marginal ranks, they are not distribution free, and they don't have the nice properties that make their univariate counterparts important inferential tools. So the question is, can we come up with a definition of, or with an ordering of RD yielding nice definitions of a distribution quantile function, and therefore their empirical counterparts, empirical quantiles, and ranks. When I mean nice, I mean nice from the statistical perspective, enjoying the properties that make the univariate univariate concepts successful tools for inference. Okay, and as the title of the talk tells you, I will propose something which is based on measure transportation theory. Now, there's a very essential fact that makes the d-dimensional case different from the one-dimensional case. Since there's no canonical ordering of the space, the ordering we will come up with that will be based on those measure transportation ideas will be distribution specific in the population and data driven in the sample. So we don't have a canonical order, so each distribution will induce its own ordering. Okay, and in the sample, each sample will produce a collection of ranks and signs, etc., ordering the observed n tuple. And therefore, the best we can go for is a situation where the empirical ordering, which is data-driven, converges to the population ordering. And this in dimension one, of course, we have, if we forget for a while that anyway the ordering is fixed, is given from left to right, well, this is the Ghivenco-Cantelli result, that the empirical distribution converges uniformly and almost surely to the population distribution function. So this is an essential property we would like also to see here. Okay, so let me start. This talk is based on several sources. Is this because of
it just takes a couple of iterations to converge.
Okay. So this is partly based on a paper that appeared in the annals last year, and there's an ongoing manuscript which is submitted, but still under transformation, adopting a different approach from the approach taken in this first paper, an approach which is more statistical decision related. Then there's a paper which is almost ready with Spanish colleagues that, as I will explain, provides smooth interpolations for the discrete measure transportation results we are having. And there's a very nice paper by Alessio Figalli which provides the continuity of the quantile contours we will define. So the problem is to provide an ordering for RD in dimension 2 and higher. And as I mentioned, this will be a distribution, a specific ordering in the population, and a sample-driven ordering in the empirical case. So this problem of coming up with multivariate extensions of the concepts of ranks and the quantiles, of course, is not new, because there's a need for that. And there have been many proposals in the literature that extend the univariate concepts to higher dimension, meaning that those papers, that literature provides you with a d-dimensional concept, and for the particular case that d is equal to 1, it reduces to the familiar situation. But everything always comes into a bundle. I mean, you have the distribution function, the quantile function, the ranks, and the empirical quantiles. Now, reducing to the traditional concept in dimension 1 is, of course, is quite is necessary in a sense. If you want to name your new concept a multivariate extension, but it's not sufficient, because what you need is a generalization, an extension that inherits the inferential properties of the univariate concepts. And so the question is, what are those properties? What should we look for when extending the univariate concept? So what are the nice properties the ranks and the signs and the quantiles? What are the nice properties they are enjoying in dimension 1 that we would like to see also in arbitrary dimension? Well, I will concentrate on the properties of ranks, but this also translates into properties for quantiles in perhaps a less a less direct way. And essentially those properties are twofold. The first one, which is probably the most obvious one, the one everybody would come up with, is distribution freeness. So the ranks are distribution free under the family of, say, all absolutely continuous distributions. Let us not look at distributions with atoms, because then it's a little bit more tricky and it's not really. So distribution freeness. This is a finite sample property of the ranks, and it is very essential because it means that everything that's measurable with respect to the ranks will be distribution free, and that provides you with statistical procedures that are valid irrespective of the underlying distribution of usually some white noise which is involved in the data generating process. So that's one thing. But that's not sufficient. I mean, it's a kind of flagship property for the ranks, but you can think of many things that are distribution free and yet don't have the nice properties of ranks. Because the ranks also are efficient. And when Wilcoxon, long time ago, we were not born, almost born, very long time ago, came up with the first rank-based procedure, the Wilcoxon test. Well, he was just looking for something to replace the traditional student test that would remain valid, that would be robust, etc. He was not expecting anything particularly powerful. But since people started using the Wilcoxon test, they realized that it was extremely powerful, surprisingly powerful. And the explanation came later on. You may remember that famous result by Hodges and Lemon, showing that if you are using normal scores, well, the normal score rank test is uniformly most powerful in the asymptotic relative efficiency sense than its student counterpart, except at the Gaussian, of course, where they are asymptotically equivalent. And the explanation came much later, and it seems that this is a property of semi-parametric models, where the semi-parametric nuisance, the infinite dimensional nuisance in the model, so you are making inference on some parameter of interest theta, which is fixed dimensional, and then there's an infinite dimensional nuisance, which is the density of some underlying white noise. There are, of course, zillions of models of that type. And, well, the best you can hope for in such a semi-parametric situation, when you are doing inference about theta, the best you can hope is provided by these semi-parametric efficiency bounds, which may be strictly less than the parametric efficiency bounds. So the difference being the cost of not knowing the underlying density. Now, if you base your inference on the ranks of the residuals, so imagine that you are testing that theta is equal to some theta naught, and you compute the residuals associated with that theta naught. So under the null, those residuals are, say, IID with some unspecified density, and under the alternative, well, they are not. So the idea is to base inference on the ranks of those residuals. Well, it can be shown that by choosing the right scores, well, you can find a test which is measurable with respect to those ranks that achieves any semi-parametric efficiency bound. So it might be that you have to estimate the underlying density in order to reach that uniformly. But if you don't want to go to density estimation or score estimation, well, you can choose your favorite score function, and then you will reach this semi-parametric efficiency bound associated with that score without sacrificing validity. And this is very different from the traditional tangent space approach, where if you do not use the correct scores, or at least something that asymptotically goes to the actual score function, then, well, you are losing validity. And the basic idea is to take the central sequence associated with your favorite density and look at the conditional expectation of that central sequence conditional on the sigma field of the residual ranks. So that is distribution free under the null, and it can be shown that, well, under the right, the correctly specified density, it is asymptotically equivalent to the semi-parametrically efficient central sequence, the one you obtain by tangent space projection. Okay, so this is what I call HW. It's a form of semi-parametric sufficiency. So when it is meaningful, of course, because all this construction requires some regularity assumption. And this is that semi-parametric efficient procedures can be based on residual rank-based statistics. So this is a combination of a finite sample property that provides you with a very, very broad, almost universal validity, and an asymptotic property that tells you that you are not losing semi-parametric efficiency in a sense. So the ranks realize this kind of compromise between validity and efficiency. And this is what we also would like to see in dimension D. So if we come with an extension of the univariate concepts, well, we would like it to satisfy those two properties. Now, the second property follows from a kind of a more primitive property of the ranks, which is related to their maximal invariance with respect to some group of transformation that generates the model. So it's maximal invariance, which I call HW star, which in the univariate case implies this semi-parametric efficiency property we would like to see there. And in this talk and in the paper I mentioned, I do not show this semi-parametric efficiency property, but I show something which is this maximal invariance, so there's still an additional step to be made. And of course, this is something I would like to do in the near future. Okay, so if you look into the literature, I mentioned many attempts to come up with something. Probably people are most eager about coming with some concept of multivariate quantile. They would like to see contours that will play the same role as quantile intervals, or quantile regions in dimension 1. But of course, there's always this kind of duality between ranks and quantiles, and here I'm talking about the ranks. So the oldest attempt to come up with ranks in a multivariate setting is component-wise rankings. So you have something in dimension D, you have marginals, and you just rank your components, and then instead of having one ranking, you have D rankings. And so you have a vector of ranks along each coordinate axis. So this has been exploited, for instance, in a big monograph by Poulinsel in 1971, but people have kept on working into that direction. And this is closely related to the idea of a copula transform, because you also uniformize, kind of uniformize the margins. And well, that's very nice, but one, those ranks are not distribution proof. And second, they are not maximum invariant under something which is big enough to generate the whole model, meaning in the space of distributions, you need a unique orbit for the group. So no, that won't do. Then there's another strand of literature on a very mathematically very nice and elegant extension of a L1 ID on the definition of quantiles. Well, this strand of literature has been followed by people like Oya, Hanu Oya, Prabal Chowdhury, Kuczynski, Choi and Marden, and many papers in that direction, because it's mathematically nice, I assume. Because as far as the properties, the statistical properties are concerned, again, well, there's no distribution freeness and there's no semi-parametric efficiency there. Then there's an approach based on Mahalanobis or pseudo-Mahalanobis ranks and signs. And I have written maybe too many papers on that topic. And basically using this, well, distribution freeness is there, semi-parametric efficiency is there, and you can basically solve all problems, classical problems in multivariate analysis that were originally designed for multivariate Gaussian observations. But validity is limited, and semi-parametric efficiency as well, is limited to the class of elliptically symmetric distributions. So indeed you have something that does the job, but not for the class of all absolutely continuous distributions, just for the class of elliptically symmetric distributions. So in a sense, that can be a model for us to extend to the general case. And in a sense, it consists in transforming the data by using the elliptical symmetry assumption. You first sphericize, and then using the empirical or population distribution, radial distribution function, you bring everything to the unit ball. So that's the type of idea we will exploit more broadly. Okay, so the problem has not been solved, despite of many attempts. So the question remains, can we come up with a concept of distribution and quantile function in RD with those properties of, so those two properties, distribution freeness and at least the maximum invariance, and with the population and sample versions related to some Glivenko-Cantelli result. So that's the question, and now let us try to answer this question. And in order to answer this question, well, the best idea is to come back to what we do know. And what we do know is the univariate case. So let us come back to the very basic univariate case, and let us look at the traditional concepts, but maybe from a different angle. It's often by turning a concept in all directions, looking from above, from below, from the side, that eventually you find the perspective that indeed will lead to a generalization. So let us revisit the traditional univariate concepts. Now, let us pause for a while. There, in the title, there's measure transportation. Some of you might be familiar with measure transportation, but perhaps not all of you. So let me give a brief account of measure transportation. Very elementary. So the story starts with Gaspard Monge in 1781, and Gaspard Monge at that time was teaching mathematics in an engineering school under the Ancien Régime, so before the French Revolution. And well, among the subjects that were in the program for the students was road construction. And when you are doing road construction, an important part of the activities consists in moving infill material, piles of sands or whatever, and you have to move them from the place where there's too much to places where you are lacking such material, meaning you have to fill holes at some other places. And so the problem is, so here is a heap of sand, and here is a hole, and they have the same volume, volume 1, and the problem is, how should I take this piece of sand, let's say, where should I take it here in order to minimize the total transportation cost? Very, very applied problem. At that time, great mathematicians did not look down to applications. And so Gaspard Monge wrote this memoir. So the infill material is déblai, and no, it's remblai, and déblai is, well, it's the same thing with a negative sign. Here is a picture of Gaspard Monge, who was also, he was not just a mathematician, he also went into politics, and he had quite a role. He was Minister of the Navy during the Directoire, and later on he went with Bonaparte in Egypt. And he was the leading force behind the creation of the École Polytechnique and the École Normale Supérieure, where he has been teaching for many years until he was forced into retirement because, having been a revolution, with the revolution, when the kings came back, he was not well, he was in trouble. So you see here is the story. So we have this pile of sand, and you have to fill in this hole here. And the simplest and most intuitive way to formulate this problem is as follows. So I will formulate it in probability terms. So let P1 and P2 be two probability measures, and let it be over a real space for simplicity. And here is a transportation cost, L. So this is a measurable loss function, L, computed at x1, x2, which are two locations in Rd. This is the cost of transporting x1 to x2. Okay? And so the idea is to find a map T of x, and the cost of the implementation of this transportation map is this. And this transportation map should not be any transportation map. It should map distribution P1 into distribution P2. And the analysts have this nice notation that T is pushing P1 forward to P2. And we statisticians would write PTX, well, P1 TX is equal to P2, meaning that if X has distribution P1, TX has distribution P2. So we want the transport T to map P1 into P2, And among all transport maps that do that job, we would like to pick the one that minimizes this transportation cost. Okay? So the problem looks simple, and a solution of that problem, this is an optimization problem, and the solution is called an optimal transport of P1 into P2. We will restrict to an L-square loss function, where the cost of transporting x1 to x2 is just the square distance between x1 and x2. I see that's a parenthesis. The parenthesis is missing here, or there's one parenthesis too much. And Monge was looking at the, not the square, but the distance in itself, which is more difficult from the analytical point of view. So this looks simple, but it is not, and Monge could not solve the problem. And it took more than a century and a half for someone to come up with a solution, and that someone was Leonid Kantorovich, who was a Russian mathematician who got Nobel Prize in Economics in 1975, precisely for his work on measured transportation, which under the Soviet system was supposed to be optimal, the problem of optimal allocation of resources. And, well, I will not enter into details, but what Kantorovich has been showing is that the solution, so there is a solution, and that solution happens to be in the class of gradients of convex function. What is the gradient of a convex function? Well, the gradient in dimension 1, when you have a convex function from R to R, well, the gradient is the derivative, and so the derivative of a convex function is just a monotone increasing transformation. And so the gradient of a convex function in dimension D, when you are mapping RD to R and take the gradient, is kind of a multivariate notion of monotonicity. Monotonicity, this calls for rankings and orderings. There's immediately something common there. And so Kantorovich looks at Monge's problem, which is an optimization problem. And he shows that, well, there exists a solution which is essentially unique, and it is in the class of gradients of convex functions. But all this makes sense only when those expectations, those expected costs are finite. And with this L2, this is for L2 loss. And with this L2 loss, this means that you need finite moments of order 2. And in a sense, this means that Kantorovich's results are not really interesting for our purpose, because of course, when defining quantiles or signs or distribution functions, we don't want to restrict to distributions with finite second order moments. But there's more, and that's a result by Robert McCann. And this is a result that was contained in his Princeton dissertation in the early 90s. And that goes one step further. And what McCann shows, he had the intuition that that problem, that transportation problem, was not so much of an optimization problem, but that it also had a geometric structure. Geometric means you don't look at distances and duality properties, etc. And what he shows is the following. So let P1 and P2 be two absolutely continuous. Again, this is in order to avoid problems. Absolutely continuous over RD. And he shows that then, no further conditions, there exists an essentially unique element in the class of gradients of convex functions, mapping P1 to P2. So no moments of order 2 here. Give me P1, give me P2. There's a unique mapping from that is mapping P1 to P2 and is the gradient of a convex function. This kind of monotone transformation. Now, if on top of that you make the assumption of finite second order moments, then this coincides with the Monge-Kantorovich solution. So it's the solution to the Monge's problem. It's the Kantorovich solution to Monge's problem. That's more interesting for us because we don't want this finite second order moment assumption. Okay, so the topic is still a very active topic in research, and well, I'm skipping it. Now let us come back to our problem, and let us come back first to the univariate case, and let us see whether we can see some use for this measure transportation result by McCann in the univariate case. So in the univariate case, I don't need to define a distribution function, the probability, of course, of a half line from minus infinity to z. And of course, it's strictly increasing, and it takes values in the interval 0, 1. And, well, as you know, it is a probability integral transformation, meaning that z has distribution function f if and only if f computed as z is uniform over 0, 1. Okay? Now, under this form, the definition of f very strongly exploits the left to right ordering of the real line. And this we cannot expect in RD. There's no left, there's no right. But what we still do have in RD, as we do in R, is the idea of something that goes from a center outward. Okay? So let us, instead of looking at the traditional f, let us look at this, which is 2f minus 1. And we define this as the center outward distribution function. It's still a distribution function because, well, all the information in f, of course, is contained in this center outward f, since this is a monotone increasing transformation. But now the regions f plus minus is giving the probability of are not half lines, are not nested half lines from minus infinity to z's. Now these are intervals which are kind of center about the median, but center not symmetrically centered, and leave to the left and to the right, meaning to the outside, equal probabilities. So they are intervals of the form quantile of order alpha divided by 2, quantile of order 1 minus alpha divided by 2. And you have such nested intervals, the probability of which is provided by such quantities here. Now we have values in minus 1 plus 1 instead of 0, 1, and this is the unit ball in R. And, well, it's easy to provide explicit values for this. And if you look now at this f plus minus, well, no, I'll come back later on with this. So that's in the population. So the traditional f and the center outward f plus minus. Now, in the sample, we have the empirical distribution function, which is based on the ordering of the real line. And actually, it is taking values over a regular grid, which is of the form 1 over n, 2 over n, 3 over n, etc. n over n. Well, we don't like this n over n because it's 1, and then when you transform back, well, you have plus infinity. This is unpleasant. We'd rather have the open interval 0, 1, and therefore, instead of dividing by n, let us divide by n plus 1. So we are the traditional empirical distribution function, except for this dividing by n plus 1 rather than n, is mapping the observations to a grid which is 1 over n plus 1, 2 over n plus 1, 3 over n plus 1. So it's a regular grid over 0, 1. Okay? Now, we have Glivenko-Cantelli, and Glivenko-Cantelli tells us that the soup between the empirical and the actual distribution function goes to 0 in absolute value, almost surely. But if you think about it, this is exactly the same as requiring that the maximum between the empirical at the observation and the actual distribution function at the observation in absolute values goes to 0 almost surely. And everything in between is an interpolation, and the traditional interpolation is with a step function, but you could interpolate in any arbitrary monotone, non-decreasing way. That would provide you with a distribution function which still would satisfy the traditional expression for Glivenko-Cantelli. So we rather will adhere to this one. Okay? So now, if you look at this center outward distribution function, well, since it's 2f minus 1, well, you also can come up with an empirical version, and the empirical version should map your observations to the unit ball, that is minus 1 plus 1, and therefore we will construct a regular grid over minus 1 plus 1, which is the transform of the regular grid on 0, 1, but now you will have 0 plus minus 1 divided by plus minus 2 divided by, etc. So you have a regular grid over the negative unit ball and another one over the positive unit ball, meaning that you have a regular grid over all the directions in the unit ball. There are only 2. Meaning that you could construct this grid by taking, so you take all the possible directions, minus 1 and plus 1. So these are points on the unit circle, and then the radius, the corresponding radius, you divide by intersecting it with circles with radii 1 over, 2 over, 3 over, etc. Now, here is a picture. So this is the traditional case where the distribution function takes value between 0 and 1, so the empirical and the actual. And this is the center outward situation where you have you are mapping to minus 1 plus 1. This is the population 1. And this is an arbitrary interpolation where interpolation has been made by step functions that are left continuous to the left-hand side of the median and right continuous to the right-hand side of the median, meaning that they are outward center continuous. They are continuous from outside. Now, what is the relation to measure transportation? Well, in both cases, think of the population. In both cases, f and to f minus 1 is monotone increasing. And it is mapping the actual distribution to a uniform distribution. Uniform over 0, 1 in the traditional case, over minus 1 plus 1 in the center outward case. And therefore, the traditional distribution function is the unique gradient of a convex function, mapping the distribution to the uniform. Similarly, the center outward distribution is the unique gradient of a convex function, mapping the actual distribution to the uniform over the unit ball. And that is a definition that readily extends to dimension D. So in dimension D, let us take as a definition of a center outward distribution. So let us take definition of a center outward distribution function as the unique gradient of a convex function mapping the actual distribution to a uniform over the unit ball. Now, uniform over the unit ball, pay attention to the fact that that does not mean Lebesgue uniform over the unit ball. What we want is something which is uniform in the directions and uniform in the distances to the center. The same situation we have in the elliptical case when we reduce to a spherical uniform, meaning that uniform over the unit ball here means the product of a uniform over the unit sphere, directions, with a uniform over the distances to the center. Okay. Now, when you have this f plus minus, where is it? Okay. When you have this center outward distribution function, which we denote with a boldface because it's a vector now, it's a point in the unit ball, well, the modulus of that distribution function is a probability. And actually, it's a probability of the contour where this distribution function takes values less than or equal than some given value. Okay, this is a probability, and then, of course, the unit vector, that is f plus minus divided by the modulus of f plus 1, this is a unit vector which provides you with a direction. Okay, so this is a direction in the unit ball version of the transformation. So this breaks into something that will have the interpretation of a probability and a direction which is a multivariate sign. Instead of -1 plus 1, now it's a point on the unit sphere. Now the question is, this is for a population concept, how shall we construct the empirical counterpart? And I see that time is running, so I will show a picture. So the idea is, again, to construct a regular grid, but now over the d-dimensional unit ball, and to map with a kind of discrete optimal transport to map the observations to that grid, the way we did in dimension 1. And let us construct that grid the same way we did over the unit ball in dimension 1. That is, we factorize n, the sample size, into a product nr times ns plus a residual n0, which will be between 0 and the minimum of nr and ns. And s will be the number of possible values for the sign, and r the number of possible values for the distance to the origin. And so we will take a regular grid of ns points over, say, the unit circle here. We are in dimension 2, so 1, 2, 3, etc., ns of them. And then we take nr circles with radii 1 over nr plus 1, 2 over nr plus 1, etc. And the intersection, those black points here, will provide us with a regular grid. What do we mean with a regular grid? We mean a grid which, as n goes to infinity, has a, if you look at the empirical, the uniform distribution over the grid, this uniform distribution goes weakly to a uniform, a continuous uniform over the unit ball. Okay? So this is the way we construct the empirical center outward distribution function. And now if you take the modulus of this empirical distribution function, what you have are those quantities. So 1 over n plus 1, 2 over n plus 1, etc. If you forget about the n plus 1, this will be ranks. So the ranks are provided by the ranks of those nested circles in the uniform version of your sample. And the signs are just the directions there. They are unit vectors. Okay? Now, here is an example where those things were computed on a kind of exotic plot. Now, it's not very clear whether those points can be considered ID from any absolutely continuous distribution. Yeah, something I forgot to mention because I'm trying to speed up is that it follows from a result by Figali that if you look at the class of all absolutely continuous distributions with non-vanishing densities, well, the corresponding center outward distributions in population are continuous mappings. So the corresponding contours, when you are fixing the modulus of your f plus minus, so it's the inverse image by the optimal transport of those nested circles in the unit ball. Okay. Well, those contours are closed, continuous, compact, nested, and they have all the nice properties you would like to see to a quantile contour. So the inverse mapping of your center outward distribution function has all the properties you are expecting from the geometry of a collection of quantile contours. They are nested and closed and continuous. Okay, so from the most central part, that part which is mapped to the center of the unit ball, to the extreme part, the extreme contours, which are mapped to the outer circles in the unit ball or spheres in the unit ball. Now, this definition of the empirical center outward distribution is only at the observations. So it does not provide you with a mapping of the full space. It only maps the observations. So the contours, when I say contour, strictly speaking, you don't see them in the empirical case as contours. They are collections of observations. And so you would like to draw a picture by interpolating those contours which are discrete. And this has been done here by cheating a little bit because it's an interpolation, but it's not clear that this interpolation is in the class of gradients of convex functions. Okay? Now, there are results. That's one of the papers I showed you at the beginning, where we show how we can construct interpolations within the class of gradients of convex functions. And we even can construct them with an optimal Lipschitz smoothness constant. So as a comparison, this is the result which is provided by half-space depth. So you are missing the geometry of the observations. Now, let us go to the results. What we need is Libre-Cantelli. We need joint distribution freeness of the ranks and the signs, and we would like to see this semi-parametric efficiency, or at least the maximal invariance property that is leading to semi-parametric efficiency. Okay, so here is the Libre-Cantelli result. So this is the center outward distribution function obtained by this mapping to the regular grid, computed at the observations. And if you take the maximum distance between the empirical and the actual value of this distribution function, well, this maximum goes to 0, almost surely Sn goes to infinity. So this is a Glivenko-Cantelli result. Now, if you look at the interpolations now, in order to have something which is defined over the complete d-dimensional space, interpolating those empirical values, well, if you use the interpolations that are provided in the paper I mentioned, then you have the same Glivenko-Cantelli result now in the soup form, if you prefer that one. So it's there. Distribution freeness. Distribution freeness is no problem. Actually, distribution freeness is there as soon as you are mapping a set of IID observations to a set of fixed values, fixed grid, in a way which is symmetric with respect to permutations. So here there is absolutely no problem. Distribution freeness is there. Then there's the invariance equivalence properties, and this is more delicate because what you are dealing with is an ordering. So you would like to see the traditional property that the quantiles of a order-preserving transformation of the observations are the order-preserving transformation of the quantiles. So the quantiles are equivariant under order-preserving transformation. And the ranks, of course, are invariant under order-preserving transformation. But this is a tautological property, because that's the very definition of an order-preserving transformation, that the ranks are invariant. Okay, so we shouldn't. Once the order does not come from outside, we shouldn't concentrate on this because it's obvious. But what's important is that the class of order-preserving transformations has this property of generating the model. Meaning that if you look at the way those transformations are pushing forward a distribution in the model, you need that this push forward has a single unique orbit in the family of distributions. And that's the important property here that we need. Now, as the order now in the sample is data-driven, quite naturally, that class of transformation preserving that order will also be data-driven. Okay? And so, well, here is this class of transformation where you are using an interpolation of the empirical center-outward distribution associated with a point, and you transform back now with an arbitrary gradient of convex function, and by doing so you are preserving the ranks and you are generating the family of all distributions in the class of absolutely continuous distributions. Okay, some pictures. So one of the problems when drawing pictures is that typically for a given distribution we don't know the analytical form of the optimal transport to the uniform, because this involves delicate Monge-Ampère partial differential equations. And well, by the way, we don't know of many analytical forms for multivariate distribution functions. If you think about it, basically they all are analytically symmetric, because that brings the problem to a univariate, defined univariate radial density. So here we chose to look at the convergence of the empirical contours to the population contours in a situation where we know what the population contours are, and this is a spherical normal distribution. So in the spherical normal distribution, of course, you have that the population contours are spheres, in this case circles, with the quantile order probability contents. And so we computed here for samples of size 100, 200, 500, etc., 5,000. We computed the empirical contours for probability contents 0.5, 0.75, and 0.9. And here is what we obtained. So for 100, you still have something fairly irregular, but think of an empirical distribution function. It does not, in the extremes, it does not fit that well on the average, the population distribution function. So there are spikes out of the population contours, but starting with 1,000, you do see the convergence, and with 5,000, definitely you have something quite reasonable. So simulations are still being performed. Here is another one, which is less satisfactory, showing that in dimension 2 you need more observations to estimate a full distribution, and that's not so much of a surprise. So this is about a mixture of 3 Gaussian distributions. Basically, there's one to the left with a negative correlation, one to the right with a positive correlation, and one in the center with horizontal main axis. And well, depending on the correlation, you see here it's -4, and here it is +4. Well, you have 3 components that are far apart, 1, 2, 3, or completely. So here you have one of the components which is of this form. The other one is oriented that way, and then there's a central one. Well, here is what you obtain with 2,000 observations, and we are a little bit disappointed that, as you can see here, it does not really descend very, very far. 2,000 is sufficient to have it redescending a little bit here, but this region here, which is empty, corresponds to one very small slice in the unit ball pizza, and that slice is empty. And the empirical transport magnifies this slice very, very significantly, but it is still empty. And when it is empty, the interpolation just jumps over. Okay, so I expect that with 5,000, you would see it redescending more clearly. Now, conclusions, well, I hope this opens the door to many, many things that we are doing in dimension 1 and would like to do in dimension D, but we're not able to really to do so far. This calls for a kind of a new empirical process theory, and there are zillions of problems you could think of working on using this concept of a distribution function, of a quantile function, rather than the univariate one. Okay. So, including functional extensions. And there's another field where this could be extremely useful. Think of directional distributions. These are distributions over the sphere, and over the sphere, definitely there's a need, but there's no, so far there's no definition for quantile regions or quantile contours. Well, with this, we can come up with data-driven quantile contours that will have a deepest point, pole, and then contours that are circling this pole in some way, but not with rotationally invariant caps, as people usually do, because there's no other way to do it so far. Thank you for your attention, and I apologize for being a little bit over the time. Thank you.
Questions?
On your last slide, at the top, you've got a name, Strasser. What result are you thinking?
This one?
Yeah. Are you thinking of a particular result or theorem?
Maybe I put this out of a list without thinking too much, but these are typical.
I'm wondering if you mean Strasser.
I probably mean non-scale. I will erase that.
So on the unipole distribution, you said it has to be rotationally uniform, and then within each direction it should be also uniform. So how is this different from? I can't see how this is different from a uniform.
Well, this means that you will have a singular density at the center, whereas uniform Lebesgue has a uniform density all over the place. Here, the density will be a function of the distance to the center.
Oh, so it's not uniform.
No, it's uniform. It's a product of a uniform over the distances and the directions. So in the center, you will have very heavy density. And
oh yeah, okay, yeah.
At zero, it's not even. It's infinite.
Yeah.
But it's just a matter of the coordinate system.
So if the sample size is proportional to the dimensionality, so this empirical contours will be mass.
Oh yes, yes. I don't think that high dimensional situations reasonably can be handled with such. I mean, just imagine estimating a density in a high dimensional situation would be. It's an impossible challenge. Well, same story here, since we are estimating the complete distribution. So I don't think it's a.
But maybe this mass will have some regular properties.
But this means that you are kind of reducing your problem, the size of your problem by having some regularity structure on the distribution.
Maybe
Did
there
I
are-
understand
Maybe there are
correctly?
special families of distributions
Yes.
that go with this definition. Nice way.
That's what we have been doing so far with the elliptical distributions. We are considering elliptical distribution because they keep the Gaussian geometry of the ellipsoids while having only a univariate density in their parameterization. And that brings things basically to a univariate problem. But in a completely general setting, you don't have that, and the complexity of the problem explodes very, very fast.